OK, bonjour. Merci d'être venu. Welcome, thank you for coming. So, let me pause a little bit to go back to the big picture. So, up to now, we have sort of looked at quantities that we want to compute to explain experiments, right? We have talked about susceptibilities, and we have talked about single particle spectral weight. So all of these are, in principle, measurable. And the Green's function is not only measurable, it's necessary to do calculations. So we're sort of setting up the formalism, and already next week we'll start to make applications to concrete models. So in the case of the single particle spectral weight, we have looked at the A, for example, of K and omega, and we have seen that it's equal to 1 over Z sum over M n of e to the minus beta km, where k is h minus mu n, plus e to the minus beta k n. And then we have the square of this matrix element. And then there's let me put the 2 pi here to save some space. 2 pi, and then we have energy conservation. So delta of omega minus km minus km. Okay. So today we will comment on this. I will sort of give you interpretation of this in terms of probabilities, and we'll spend some time to talk about this. And this was a measurable quantity in the sense that we saw that the differential cross-section for angle resolved photoemission experiment was proportional to something that we that is just the integral from minus infinity to infinity dt e to the I omega t times c dagger k parallel, well, k parallel was in the plane, and then ck parallel of t. And this we will call I times g lesser of k and omega. So g lesser because it's as if, you know, if we were thinking of a time ordered product, it's as if this time was before this one. So that's why it's called g lesser. G greater will be the other direction. It's just notation, but it's standard, so I just want to tell you. And we saw that this quantity that is observable is then just f of omega, where f is the Fermi function, times the spectral weight, A of k parallel omega. And this I have shown using the spectral representation. Yes. So today I will, this fluctuation dissipation theorem, I will prove again this relation using a different trick. It's just another way to prove the same thing, just so that we stay familiar with the methods that are used to do things. Excuse me. And in the discussing experiments, I will talk also about quasi-particles. Now, this quantity that is observable and directly related to the retarded Green's function, because we had that G retarded of K and omega was equal to integral d omega prime over 2 pi of A of K and omega prime divided by omega plus I eta minus omega prime. Sorry. So we also showed that if we, instead of defining this retarded Green's function, if instead we define we define the Matsubara Green's function, G of K IKN, then it's equal to integral d omega prime over 2 pi of A of K omega prime divided by IKN minus omega prime. Okay. So this I mean everything is related to this A. And this A can be measured, or at least the negative energy part, because the Fermi function at zero temperature vanishes for positive frequencies. So this quantity that is convenient to manipulate for calculations is related directly to this. So in the first part of the class, we discussed instead the susceptibilities, right? We said that the susceptibility for two observable, I write AI, AJ here, so that can be, for example, density, current, whatever, some observable, and the index I here contains position and whatever is needed. So this chi retarded of omega was equal to integral d omega prime over pi of chi double prime of AI AJ of omega prime divided by omega prime minus omega plus I eta. So this was a commutator. This is an anti-commutator. But we saw that the physics, again, using the spectral representation, the physics is in this object. Okay. Now, since it will be easy to do calculations with this Matsubara function, we may ask, what happens to this? Is there the equivalent of, of this relation for this? And the answer is yes. So you can write this in Matsubara space as well. So if you write that chi of Matsubara, I don't know how to do that. Let's write it like this. Of AI AJ of tau is equal to, if I put the h bar, because we worked a lot with taking h bar different from 1 in when we talked about this, so let me put the h bar back, is equal to the time ordered product of AI of tau times AJ. But this time, the time-ordered product, because these are bosonic quantities, in other words, they commute instead of anti-commuting, like for fermions, then this time-ordered product is defined with a plus sign. So, excuse me, so if tau is less than 0, we put the operators in the other order. And yeah, there's no minus sign in that case. Yeah, I'm sorry. That's just the opposite. Yeah, this is this. Yeah, right. There's no minus sign. Sorry. Okay. So, and then the question is whether we can relate this object to this. And the answer is yes. The answer is that we will find that the chi of AI AJ of some Matsubara frequency, IQN, will be equal to integral d omega prime over pi of chi double prime of AI AJ of omega prime divided by IQN minus omega prime. Sorry, the other way around. Omega prime minus IQN. Just like here. Okay, so as before, we will be able to just do the analytic continuation, replaced by IQN by omega plus ieta. And then chi double prime, we can find, like you did in homework, for example, we can find either by taking the imaginary part here, or more generally, by looking at the discontinuity along the cut. Okay. So now, what I need to do is to tell you a little bit what happens here. I mean, what is this IQN? This IQN turns out to be even 2n times pi t, no 1. So for bosons, you get even Matsubara frequencies, and for fermion, odd Matsubara frequencies. And the reason is just that this thing has periodic properties instead of anti-periodic like here. Okay. So I will take a few minutes to show you just this, that this is periodic instead of being anti-periodic. And so automatically, the formulas here will be the same, except for the fact that in the case of bosonic quantities like this, we have even Matsubara frequency. So I only need to show you that this is periodic instead of anti-periodic. And then to show that, to go from here to there, what you do is just you as we did before. I will not do the proof this time. You just use the layman representation, which is just inserting complete set of states and writing explicitly the trace. So you use the layman representation to show that if you have this definition, then if you take this, then you get this, where chi double prime will be exactly what we had before. In fact, chi double prime looks a lot like this, except it has a minus sign. And instead of having this destruction operator, it has AI. Is that clear? So we basically have most of the formalism that we need. So let me take just a few minutes to talk about this. And you will see that linear response is very easy if you use these quantities. Don't hesitate if you have questions. Huh? Okay, so let's write this. Let's assume that tau is less than 0. And let's write explicitly 1 over, well, h bar, okay, 1 over h bar times, so we have sum over n of e to the minus beta k n divided by z times n times e to the no, let me not write it like this. Sorry, I will do this a little bit differently. N e to the minus beta k divided by z, so that's the density matrix, and then ai of t is e to the k tau times ai times e to the minus k tau, and that is aj. Okay. Now let me so that's this quantity. Now let's compute chi of ai aj of tau plus beta. Then I get 1 over h bar.
Just to be sure of two things. First, isn't there an n missing in the
yes,
question
and
above?
thank you.
Also, isn't showing the periodicity of this function the homework?
Did I give this as homework? I forgot now.
Yeah, I'm pretty sure.
Okay.
Well, it's not exactly this,
but it's quite close.
It's quite
exactly.
close.
We have to prove
Okay.
for bosonic the green function.
Yes.
So it's basically the same.
So let me do this very quickly then. Yeah, sorry, it's terrible. I forgot this. Of tau plus beta ai e to the minus k of tau plus beta, and I have aj of n, and I have this e to the minus beta k, and now the ai I can use the periodic property of the trace to put this this aj here, and I can put e to the minus beta k and e to the beta k, right? Because this times this is unity. Now you see that the beta k here will cancel, and I get the ai of tau. What will be left here is ai of tau. So I will have aj ai of tau, and tau plus beta now is larger than 0. So oh, sorry, I got it wrong. So here I started with tau plus beta, so I should have put it in the other order. So the proof is wrong, but you see the cyclic property, okay? So then it means that, so I should have started here by having this I should have started by having this in the wrong order. AJ and then this on this side and then the AJ over there. Yeah, so they change order, they change the side and okay. So that was an easy proof that I managed to do wrong. But you see the idea, okay? Okay. Now, what happens to linear response theory in this context? Suppose that, so I'm going to this part here, linear response. So suppose that I have an external, just a scalar potential, okay? So the scalar potential couples to matter like this. So d cube r prime, phi of r prime tau times rho of r prime. So now what I do to evaluate, for example, to evaluate the current at point r and at time tau in a non-equilibrium, then if I use the if I use just what we saw for the interaction representation, okay? So in the interaction representation, it means that if I express this in the interaction representation, it will be equal to the time-ordered product of e to the minus integral from 0 to beta d tau phi of r prime tau rho of r prime. So let me put a prime here to make it different from this, times j of r tau. So I just go to the interaction representation, and then this is the time-ordered product. Now you see, if I expand this to first order, then what I will get is, and I forgot the integral d cube r prime. What I will get is just to first order will be minus time-ordered product of the integral from 0 to beta d tau prime integral d cube r prime of rho of r prime tau. Now phi is just some scalar, it commutes with everything, tau prime, and g of r tau times phi of r prime tau prime. So you see, it's a convolution. This depends on r minus r prime, and this depends on tau minus tau prime. And so it's a convolution with this object, which means that I can write this. If I go to Fourier now, I can write the j of the q iqn using this with even Matsubara frequencies is equal to minus. So this is the susceptibility for rho and j of q IQN phi of Q IQN. Now you see that if you just do the analytic continuation of this, you get exactly what we had before. Okay? So
I might have missed it, but how did we get to the second to last equation?
Said this one?
No, to the second one.
This one?
Yeah.
We just expand this to first order.
Oh, okay. Okay, thank you.
So is everybody on board? Okay. So let's discuss now angle result photoemission and quasi-particles. So let's go back to this. Now you see that what is the spectral weight if we have free particles? Do you remember? It's just 2 pi times delta of omega minus epsilon k. Remember that? Okay, how does that come out? Well, you see that what will happen here is that when we have free particles, it means that the eigenstates here are just, you just think of filling a Fermi sea, okay? So there will be just one possibility here, to have non-zero matrix element. It will be that this state here has one less particle in state K than this one. And all the other states that don't have this quantum number in, I mean, the transition is 0. So you see, you get delta of omega minus epsilon k. Epsilon k is the difference in energy between these two states when you remove a particle. Oops. Too enthusiastic here. And you see the energy variable is this, is omega. It's not k squared over 2m or epsilon k or whatever, it's omega. And what does it correspond to? It corresponds to the difference between in energy of these two energy eigenstates. Okay, so that's like the Bohr correspondence principle, that the frequency that you measure is equal to energy differences. Now the other thing is that if I integrate, you remember that A of k omega was just a Fourier transform dt e to the I omega t of the anti-commutator of ck of t c dagger k. So it means that if I integrate over all frequencies, I get a delta of time. I can do the integral, I get an equal time anti-commutator, so I get unity. So there is so there's a sum rule already. And also, you know that if I expand, if I go back to the spectral representation for the Green's function, and I expand to, I go to high frequencies, the spectral representation was that the G of k ikn was equal to integral the omega prime. I had this equation earlier, over 2 pi of A of K and omega prime divided by IKN minus omega prime. So at the very large frequencies, when this, in fact, so large that this quantity vanishes, then it means that I can expand this in powers of 1 over IKN, 1 over IKN squared, etc. So the first term is this. So it means that this high frequency expansion starts by 1 over IKN. And this one is intimately related to the anti-commutation relations. You follow me? Okay. So, okay, back to this. When we interpret
Is it just me or is the video dead?
No, the sound is dead, yeah.
Yeah, we cannot hear you. We can hear you now. Your sound cut for a few seconds, so we just missed all you just explained.
Okay, I was starting to explain this, right?
It cut just before that.
Okay, here all I said is that the at high frequencies, the first term is this. So I can drop the omega prime. Then I will have terms of omega prime over IKN square, etc., etc. But the first term is this, and I was saying the 1 here is intimately related to the fact that if I integrate this over frequency, I get the equal time commutator, and it's equal to 1. Okay, that's all I was saying.
Yes.
So the spectral weight has an integral of 1. If I divide, I mean, the spectral weight, I mean, an integral of d omega prime over 2 pi. This is 2 pi. But so what I'm saying is that A of k and omega prime divided by 2 pi can be interpreted as a probability distribution. It's the probability that a particle or a hole in state K has an energy omega. Particle or a hole in state K has an energy omega. So let's say this creates a hole, okay? A hole in state K on an eigenstate M. Now this eigenstate M of energy is not an eigenstate of K in general. Because if we have interactions, potential energy and kinetic energy don't commute. So the eigenstates, these M and N that are energy eigenstates, are not eigenstates of K. They, in general, have some linear combination of Slater determinants. We talked about that if you want. And some of which contain this C of K. And same thing for this. So in general, these energy eigenstates, and we will see a real example later. When I have K here, sorry, omega, and I ask for the probability that it has, let's say, K squared over 2m. Well, it's not a delta function, it has a width. It says that there are many states here that are near what the free energy state, the non-interacting state was, that have a non-zero overlap. And again, because it's normalized to unity, it means I can interpret this as a probability. And in fact, it is, because if you look at this cross section, we said that this was we said that it was f of omega. I mean, there are all sorts of factors here, but if we focus on this was f of omega times a of k and omega. So that's the probability there's a particle in state k that has an energy omega, but there's a Fermi factor also in front. So at 0 temperature, this f of omega is 1 or 0. It's 1 for negative energies. So it means that we are looking at holes only. And we're looking at the probability that the whole of quantity of momentum k has an energy omega that's negative. Is that clear? Yes. Okay. So I will show you some experimental results. But before I do that, I just want to show you this. Okay, you see that here, this A is an anti-commutator, right? So this is just one piece. This is just one piece of that. Okay, it is the piece where I've reversed these quantities. So again, we can show the fluctuation dissipation theorem, but using some other kind of proof. So if I use a trace, so let me write this object here. So I want to write the sum d omega. I'm sorry, the other. Which piece do I want to write first? Yeah, let me write this piece and relate it to the other order. Well, it doesn't matter. Sum d omega over 2 pi. Sorry, integral dt. Integral dt e to the I omega t of a trace of rho. So I have e to the minus beta k times the c dagger k parallel. I'm sorry, yes, exactly. And then the time evolution is here. So I have e to the I k t ck parallel e to the minus I k t, and that's it. So now, as usual, I can use the cyclic property of the trace, and I can put this here. So I can take this old block here and put it here. E to the minus beta k times the c dagger k parallel. And now to have this correctly here, e to the minus beta k, I can put the identity here, e to the beta k. So you see that what happens is that what I get is the integral dt e to the I omega t there was a Z there, times the average here of C K parallel of T minus I beta times the C Okay. So I was saying that you see if I look at the other order, which is that well, now it's erased, but I can relate the quantities in this order Fourier transform, and in the other order just by this e to the minus beta omega. That's all I was saying. And if you work it out, it means that you can, here you have the two pieces, here you have only one, but here you have only one, but you can take care of that with this Fermi function. Okay, so now I was going to show you some experiments. So first I will share my screen. Okay, so you see the experiment?
Yeah,
Yes.
there's a graph energy
Yeah.
relative to EF.
Okay,
And
so this is the intensity, so it's proportional to F of omega times A of K and omega. And so here we know that, so this is, what is varying here is the angle of the ejected photoelectron. Okay. So the angle basically tells us K parallel, because we are coming with a photon that has pretty high energy. So the electron that comes out has less energy than the photon, because it was sort of below the Fermi surface, but still comparable to the energy of the photon. Okay, so it has energy comparable to the energy of the photon, which means that the length of the vector k is does not vary very much when you change omega. But if you change the angle with respect to the plane, then it's you're measuring k parallel. Okay, so it is labeled with angles here, but it is really a measure of k parallel. And the energy here is on this this axis, and kf is this is in this region, is around 14 degree, and if you're at 13 degree, you're outside the Fermi surface, but there's still some weight because the calculation, this is done at finite temperature, so the Fermi function still has some finite overlap with positive. I mean, it does not vanish for positive frequencies, but the magnitude of the cross section here is multiplied by a factor of 16 to be roughly the same size as the other quantities. So you see that as we get closer to the Fermi surface, so moving this way, like I don't know if you see my mouse here, but moving this way,
Yeah,
you're getting closer to the Fermi surface, and the peak is becoming narrower. It's not becoming infinitely sharp, because there are finite temperature effects and because there's finite energy resolution here. That's about 35 MeV is the energy resolution. So the point I want to show is that even though you have a specific K parallel, you have several energies that overlap with that. We don't have a delta function, but it's becoming narrower as we get closer to the Fermi surface. So I will show you that in the second class. I will show you what that means. And then the fits are Fermi liquid fits, and I will explain what I mean by Fermi liquid fits. And you see that the peaks are not completely symmetric, and that's also expected from Fermi liquid theory. Now, if I look at, so these are called energy distribution curve in the jargon, because they give the cross-section or the probability as a function of energy. Now, if you look at this, these are momentum distribution curves. Here, this one. These are still energy distribution curve, but these are momentum distribution curves. So it means that we are looking at a fixed energy. So omega is fixed. Is as if in this plot here we fix omega and we change the wave vector. So at omega equals 0, you get this in the Brillouin zone. So what is this compound? This compound is strontium ruthenate, which is quite famous, and there's still some research in my group and other groups on this, and the strontium ruthenate. And you see here, these are the energy distribution curves. So this experiment here was done in 1992. So the high temperature superconductors were discovered in 1986-7. And they turned out to be very two-dimensional. So people started to do a lot of angle result photoemission experiments on them, and the instruments developed. And in fact, at that time, even there was no compound that had a clear Fermi liquid behavior. I will explain again what is a Fermi liquid next class. And this compound here, TITE2, was the first compound where they could show a fit with the Fermi liquid parameters. They don't quite fit the calculation of the electron gas that I will show you. The damping seems to be larger than what simple electron gas calculations give. But yes, that was the first compound that had the Fermi liquid behavior. Now, these experiments here are done in 2000. So they're more refined. You see that there's not a single Fermi surface. There are three Fermi surfaces here. And you see the energy distribution curves have much narrower features, and they have many more angles that they can measure. And here is an even more recent experiment that's 2019 in the Physical Review X, where you see the same Fermi surface, going from 2000 to 2019. You see how much accuracy we have now. And these are, again, momentum distribution curves, but for different energies below the Fermi surface. So you can see the dispersion of quasi-particles. I will explain what a quasi-particle is. I mean, these are, you're detecting electrons, but you're measuring quasi-particle properties. And clearly here, I forgot to mention, but the strontium ruthenate is also very, very anisotropic, so mostly two-dimensional, and it has a square lattice. So that's why the Brillouin zone is just a square like this. And if you look at high temperature superconductors, this is 1/4 of the Brillouin zone. So it's as if we were looking at just one of these quadrants here. You see that it's as if we were missing a piece of the Fermi surface. This is a very strange property of high temperature superconductors. Contrary to here, where we see every piece of the Fermi surface. And again, if we stick with this strontium ruthenate, and we look at, this is now energy as a function of wave vector, k parallel, but in certain direction, preferred direction, in the Brillouin zone. And you see that energy as a function of k. The experiments, they are the red dots, and the calculations are the colored quantities. And these calculations are done with modern electronic structure calculation, including correlation effects. So we've gone to these rather primitive experiments in some way, but that could measure Fermi liquid behavior. But with widths, the widths were not quite in agreement with theory. So these quite sophisticated results. So that's electronic structure calculations plus dynamical mean field theory that I will explain also in the class. So these are energy distribution curve, momentum distribution curves, and this is a different representation of the same data. Okay. So are there any questions? Okay, so I will stop here. And I have put a new version of the notes. I mean, these plots I just showed were not in the original notes. So this new version of the notes contains these plots. So we will, next class, we will talk about quasi-particles. We will think a little bit more about these things that, that they have a probability that's maximum around some wave vector, but not quite. So they're not particles, they're quasi-particles. And we will talk about Fermi liquid theory, which is a way to describe these quasi-particles and tell us their properties. And in fact, one of the reasons that the non-interacting electron model plus collisions as such a success is because Fermi liquid theory applies. So I will explain to you the basis of Fermi liquid theory also. Okay. Are there any questions?
Yes.
Okay. So we'll see you next Friday at 10.
Okay, see ya.
I will stay if you have questions.